Now, when you're solving equations, sometimes you have unique solutions, which means there's exactly one. Sometimes you find that there's many solutions, so there's more than one possible value for the variable. And sometimes there's not any. I'm going to show you what each one of those, well, I'm not going to show what the many solutions look like yet, but we'll get to that. But right now I'm going to show you what it looks like to have a unique solution or no solution at all. So I'm going to try to solve these two equations here. And mostly it's just applying the order of operations, something that you've already practiced a bunch. So this is really not anything new, it's just the last little step has got a new concept in it. 4 squared is 16 minus 10 plus n equals 10. 16 minus 10 is 6. 7 minus 6 plus n equals 10. 7 minus 6 is 1 plus n equals 10. So since we really haven't learned any operations on the equations yet, this statement here is really asking the question, what plus 1 is 10? And the answer to that is 9, of course. N equals 9. That is a unique solution to this equation. You might, since you probably have all taken Algebra 1 once before, maybe pre-algebra, you've probably seen this. When I have a nice one-step equation here, I can subtract 1 from both sides, and I get n equals 9. But that's not necessarily something that you know yet, so you just have to ask yourself what 1 plus what is 10. The what has to be 9. Next problem. Ooh, looks like I got some distribution to do here. N times 3 is 3n plus 2n plus 6 equals 5n plus 10 minus 3 is 7. Combine like terms here, I get 5n plus 6 equals 5n plus 7. This is a problem. No matter what number I plug in for n, let's try 1. 1 times 5 is 5 plus 6 equals 1 times 5, which is 5 plus 7. Well, there's no way that 11 will ever equal 12. If I plug in 2, it's not going to work. If I plug in 3, it's not going to work. And the problem comes from the variable parts matching, but the constant terms not matching. That right there has to be a red flag should go off, warning bells, big klaxon siren should go on off in your head. That's a problem. If you remember the simple steps from geometry before, I could subtract 5n from both sides and I get 6 equals 7, and that's never true. But just by noticing that the variable term is the same, but the constant term is different, that should tell you that there is no solution. And the way we show that in the in set notation is something called the empty set, which just looks like a big 0 with a diagonal line cut through it. This is called the empty set here. Now, if you want to write that down, instead of writing down no solution, you're welcome to. I abbreviate no solution, no SOL apostrophe N. So either one of those would be an acceptable answer to share for this kind of problem. But it really came down to the expression, the algebraic term matched, the constant term did not. That always causes a problem. Here's an example of what can happen when you might have many, or an infinite number of solutions that are true. So, and we call this the identity. I got my big expression here. It's got all kinds of parentheses. It looks like I got a lot of work to do with order of operations. But once I get down to that, then it'll just be some basic stuff. So let's start applying some order of operations here. 2 times 5 is 10 minus 8. 3h plus 6. That's nothing's going to simplify there for now. 2h plus 5 plus 6, associative property. I can add that 5 and 6 together, and I get 2h plus 11 times 2. Alright, that's some distributive property I'm going to do in a second here. 10 minus 8 is 2. 3h plus 6. And what do I got here? I got 6h altogether plus 12. Okay. I might have written this problem down wrong from the book. Let me double check. Oh, I did. Okay. So, mistakes. Here's how to handle mistakes, if I haven't already talked about it inside of the lecture part of the class. I wrote the example down wrong. So what I'm going to do, instead of erasing everything, because I've already done a bunch of work, I know when I'm looking back at that example that that part is written incorrectly. So what I'm going to do is I'm going to go back and do 2 times 5 minus 8, 3h plus 6 equals 2h plus h plus 6 times 2. Now, you can see I did fix that one part that was the same. And I'm going to do a simple line through all this other work to show that that's all incorrect work. Notice I'm not erasing it. And the reason why I'm not erasing it is because I've already done a bunch of work, and some of it might not have been bad work. Like, did I write anything wrong down on the left-hand side? No. So do I know what this all reduces down to already? Yeah. All this stuff here on the left-hand side reduces down to 6h plus 12. I've already done all that work. Since I didn't erase it, I know what it's supposed to be, and I can leave it there. So now all I got to do is redo the work on the part that I messed up on when I was translating the problem from the book to the, in my case, the computer or the page. All right, 2h plus h is 3h plus 6 times 2. Now I'm going to distribute that. 2 times 3, well, let me just rewrite this first. 2 times 3 is 6h. 2 times 6 is 12. There we go. Well, take a look at this problem here. Notice how both sides are exactly the same. That's what an identity is. Identity means self, right? So each side of the equation is itself. That's going to tell me that there are infinitely many solutions. You can, of course, abbreviate that IMS. If you're looking for a simple symbol, a simple symbol to represent this, I mean, the infinity sign exists for this, but it doesn't actually work in this scenario. So there's really not a nice way to write it down. Maybe if you wrote it in set notation, like if you wrote the solution set is actually is infinity, but that's cumbersome. IMS for infinitely many solutions works just fine. All right, next video, more examples.